approach the same on either side, or there are other situations that are specific to DNE. So what will you say? As X approaches, look at the target, just follow the mouse.
Infinity.
I'm sorry?
Infinite?
Yes, of course. As X approaches 1 from the left, the function value has a target of infinity. Perfect. Excellent. So now, 1 from the right. 1 from the right. Look at the target, where the function is going.
Be negative infinity.
Excellent. And the final question, the limit as X approaches 1 from either side.
This one is DNE.
Indeed. This one is DNE because the left goes to infinity, positive infinity. The right goes to negative infinity. This must be DNE, indeed. Perfect. Okay, I like to look at, so you know why we refreshed our memory on piecewise defined functions for this. So let's look at 77. And we have h of x equals x plus 1 for x less than 0. We have 2 for x between 0 and 1. And we have 3 minus x for x greater equal to 1. Some of your work was not acceptable on the piecewise defined function, so please look at the solutions and please pay attention to what we're doing now, if you didn't before. So the first thing is we have to change this into the interval notation. Then we have to change this into the interval notation. And then we have to change this into the interval notation. Looking at, oh, I'm sorry, I wrote f of x. I'm going to change this into f of x. So looking here, can anyone identify the domain of this function?
Parallel numbers.
Yes, indeed. Nothing is missing. Everything to the left of 0, 0. Everything between 0 and 1, 1. And everything between 1 and infinite. Excellent. Yes, 0 and 1 have to be in the table. I have to write underneath 0 an open parenthesis to the left, a bracket to the right. Again, the same thing, 0, parenthesis under 1 and bracket to the other side. I will make myself a note so I don't make a mistake because these may not be in the correct order. X plus 1 to the right of 0. 2 in between 0 and 1. And 3 minus x from 1 to infinity. So this will be one graph, this will be another, and this will be the third. They will not overlap. Good. So I'll plug in -1 to get 0. I'll plug in 0 to get 1 inside the parenthesis. I don't have anything to plug in, so this is just 2 all over. I plug in 1, it's 2, and I plug in 3, and I get 0. These are linear functions, so I needed 2 points in each. I already, without even graphing, can anyone tell us what is the limit as x approaches 0 from the left of this function? Limit, that's why this is such a crucial table. X approaches 0 from the right of f of x. Limit as x approaches 1 from the left. Limit as x approaches 1 from the right. And of course the limit as x approaches 0 from either side. And limit as x approaches, 1 from either side. Just look at the table. We haven't even graphed it. We don't even need to. We will graph it, but we don't even need to in order to determine these limits. Can anyone give us, by looking at the table, what is the limit, the tendency, the target of the function as x approaches 0 from the left?
Is it 1?
Indeed, it's right here. Even if it's an open point, we're not interested in the function value. Who said that? Thank you. I appreciate it.
Me.
Thank you. Good. The limit of f of x as x approaches 0 from the right.
2.
Indeed. What will you say about the limit as x approaches 0 from either side?
D and E.
Indeed. I have no number. I have to have a unique number. I don't. The left-hand side goes to 1, the right-hand side goes to 2. I cannot have a number here. They are not equal. Good. Limit of f of x as x approaches 1 from the left.
Two.
Perfect. Limit as f of x as x approaches 1 from the right.
Is it still 2?
Excellent. The limit of f of x as x approaches 1 from either side.
Two.
Indeed, because they are the same. Excellent. Okay, finally, let's graph it. See how useful the table is? That's why I want you to get used to it. It's really a piece of cake. It's really nothing. Really nothing. -1, 0. -1 for x, 0 for y. 0, 1. With an open point. Why? Because it's a parenthesis. That's why it's an open point. That's done. 0, 2. With a pool point. 1, 2. But it should be open. Okay, fine. That's the middle part. But now 1, 2 will go in and fill it in. 2, 3. You do not have to use 3 colors. The reason I use 3 colors is because I don't want to see this. It's not going to be a function if you graph something like that. There is no need for you to use 3 colors. I'm just making a point. It's very clear. As x approaches 1 from either side, the function values approach 2. As x approaches 0 from either side, as you see 0 from either side, this side goes to 2 and this side goes to 1. Because there is a jump. Jump. The jump is at 0. Okay. Now, I'd like to move on to determining limits from functions, not from graphs. So that's 1.2. Okay, so I'd like to just directly, any questions, please don't let me move on if you have questions. Okay, I'm sharing and 124. Okay, so there is a theorem that I would like to explain on rational functions and polynomial functions. So that's where the starting point is. Limit of a polynomial. Limit of a polynomial. I'm going to call the polynomial p of x. As x approaches a from a is any number, is p of a. And you can say, but wait a minute, you're just contradicting yourself. You just told us that you're not looking for the function value. And you're saying now that the limit is the function value. It just happens to be that way for polynomials. So for example, if I have the limit as x approaches 2 from x squared plus 2x minus 1, it happens that is the polynomial evaluated at 2. If it can be to the right or to the left or either side. So it's going to be 4 plus 4 minus 1 is 7. It just happens that way. But still, this operator says the target. It happens that it's the same with the function value. Okay. Now the limit of a rational function as x approaches a, I'm going to denote the rational function, let's say p of x over q of x, is p of a over q of a. There is a catch. If q of a does not equal 0, of course. We discussed domain last time of rational functions. Rational functions don't exist if the denominator is 0. So I can plug in and get the value, but only if a is in the domain of the rational function. If it's not, I cannot do this. So you can say again, you're contradicting yourself. You just told us you're not looking for the function value. True. But it just happens that for polynomials and for rational functions, I can plug it in, but here there is a catch. Here there is nothing. It will always be that. But here there is a catch, because if the denominator is 0, then I can do this. So here's an example. So let's say I have limit as x approaches 1 from x plus 2 over x plus 3. 1 is in the domain. I can straightforwardly plug it in. So this is 3 over 4, and it's done. Why? Because it happens that 1 is in the domain of this function. And for rational functions, I can simply plug it in if 1 is in the domain and get the limit. It happens that it's, in this case, is the same with the function value. Now, what do I do in this situation? Let's say I have limit as x approaches 3 from the right, from a 3 plus 9 over x minus 3. And this is trouble. Big one. So every time I am asked to find the limit, I have to, most of the time, 99% of the cases, I have to plug it in. So my first step is plug in. And you can say, but you just told us that. I know. But I have to check the type of limit I'm facing. Here I plugged it in. Done. Here I have to plug it in. And when I plug it in, here's what I need to write. 3 plus 3 is 6. 3 minus 3 is 0. That's why this is trouble. Because we know that 6 over 0 is undefined. That's why I say it's trouble. Here it was nice, because 3 is not in the domain of this function. 3 creates this, turns this into an undefined situation. So 6 over 0, what are the options? There are 3 possibilities, but definitely no hope. No hope. The limit can never exist. In the situation of a number over 0, there is never hope. So the answer are infinity, negative infinity, or D and E. This is a dead in the water situation. So what do I write? I can't write all three. Here's what I do next. I realize that the numerator will be positive no matter what. 3 from the right. I'm thinking of a number very close to 3 from the right, larger than 3. I'm thinking of 3.1. 3 plus 3 plus 0.1 is still a positive number. I need the sign. You can say the sign of 0. Yes. I need the sign of 0 by you plugging 3.1 in here and just tell me the sign. Don't calculate anything. I only need the sign. As if you plug in 3.1 and subtract 3. I just need the sign.
Positive.
Indeed. So then, and I can only choose one, which of these 3 options will I choose in this particular case? I can only choose one.
Is it infinity?
Exactly, because it's positive over positive. Let's look at another one. Limit Sx approaches 1 from the left, from x plus 1 over x squared minus 1. Do I want plus 1? Yes, I want plus 1. Yeah. I don't know what this is. I have to plug it in first because I don't know what I'm facing. I don't know what type of limit this is. So first I'm going to plug it in. And on top of the equal symbol and in the bottom of the equal symbol, below and up, above, I'm going to write what I find. When I plug in 1 plus 1, I get 2. When I plug in 1 minus 1, I get 0. I know trouble. I know no hope. I know infinity, negative infinity, or DNE. This is a dead situation. Dead in the water. Okay. I realize that I can factor the denominator. So let's see if that helps. Can anyone factor the denominator for us?
X plus 1 and x minus 1.
Very good. Thank you, Daisy. Nice to simplify, if I can, always. And limit Sx approaches 1 from the left of 1 over x minus 1. The numerator is still 1. The denominator is still 0. But I need the sign of 0. Sign of 0? Yes. 1 from the left, a number very close to 1 from the left is 0.9. Don't go to negative 15. Very close to 1 from the left. Please imagine that you plug it in and you just simply give me the sign of that 0. I don't care to calculate anything. I just need the sign of that 0.
It'd be negative.
Good. So then I have to choose. I can only choose one. What is the answer?
Negative infinity?
Absolutely. Because the top is positive and the denominator is negative. And this is a situation of no hope. Absolutely never and ever. No hope means this, this, or this. And in this case, the top is positive, the bottom is negative because I had to enter a number, at least imagine I enter a number, close to 1 from the left. Close to 1 from the left is 0.9. The numerator stays positive, the denominator will be negative, so then the answer is negative infinity. Any questions? Any questions?
So when is it DNE?
Okay, very good. So limit Sx approaches 1 from the right of the same thing. So this is positive and this is 0. This is 1 and 0. Can anyone plug in 1.1 and give us the sign of 0 in the denominator?
Positive.
Good. So then the answer is, this is no hope. We know what the options are.
Positive infinity.
Good.
Negative infinity.
You can only choose one. You cannot choose more than one. It's positive over positive. It could never be negative infinity. And final question. X approaches 1 from either side of this. Since I was asked, when is it D&E? The limit from the left is negative infinity. The limit from the right is infinity. So then what do we conclude about either side?
D&E.
That's it. That's it. Any questions? Okay, so well, just because before I forget, R.5 is complete, 1.1 is complete. So these have to be completed with 70%, and then you can work on them till we take the test. You do whatever you want, but with 70% by Wednesday before class. I did not, I'm not even halfway through 1.2. But I will assign something from 1.3 because 1.3 was completed. It's all about the average rate of change, and it's just one problem. We don't have to worry about 1.3. And so these 3 sections have to be completed. Only with 70%. You don't have to worry about more. You can work on those later on. But we need 70% so we can move on as a group, please. Will you stay?